Uh, Hello, everyone. My name is Lino. I'm chair of this section. We're going to have 3 presentations now in this technical section too. The first talk is going to be a advice paper. Is given by Daniel Varela Magalhães from IFSP São Carlos. The title of his work is an extended cavity diode laser contributed with additive manufacturing contribution for a Brazilian compact atomic frequency standard with cold atom. Daniel, the stage is yours. You have a half hour for your presentation.
Okay, Lino, thank you. And thanks to everybody that is watching this. I'm not seeing you, so if you need something, Lino, you have to unmute your microphone. So this was supposed to be a very simple task in our lab. I'm going to show you a general view of our lab, and then to justify why we went to this development of additive manufacturing is the nice name for 3D printing. So I'll give the details. This is something that we did within the framework of our research center. That's a CEPID from FAPESP. It's called the Research Center of Optics and Photonics. And there are a lot of people involved because we had a thesis and some other researchers involved because of the different areas for this specific topic. Okay, then let's go on. Just to introduce you, an atomic frequency standard is, let's say, simply a feedback system or a closed loop system that takes an atomic transition as a reference and servo lock a macroscopic oscillator. Okay, this can be in the microwave domain if we have a clock transition in the microwave domain, of course. But nowadays we have, from some time, we have already some clock transitions in the optical domain. And so this macroscopic oscillator is the frequency generator, let's say, is a laser, a very stable laser. Once we get this servo loop, we can extract time signals to accumulate these tic-tacs, or we have frequency signals to use as a reference for calibration. And I give you some examples of applications. Okay, and so that's not every atomic transition that is eligible for a clock transition. So a clock transition should be some specific transitions that have a long lifetime, so you decrease the line width of the resonance, the observed resonance when you have it. Okay. One of the main goals of these atomic frequency standards is to promote general distribution coordinate of time. That's called the UTC, and there is also the specific UTC is merged, a merge between TAI, International Atomic Time, and the astronomic time. So then you get what we had in the past as a Greenwich time. That's not called this anymore. So we have UTC BIPM, that's the central reference, and each laboratory around the world that contributes with UTC for the UTC formation has his own UTC or local UTC. So you have UTC PTB, UTC NIST, UTC LRT. That's our lab here. This is the map distributed by BIPM with all the contributors for the UTC. We are appearing at USP from the end of 2018, because we are already, from that time, we are contributors, regular contributors for UTC. This is our infrastructure here in São Carlos. We belong to the campus of São Carlos of USP. So we have here some commercial clocks, or commercial atomic frequency standards. Clocks sometimes is a nickname that we use to simplify. And these commercial standards are maintained 7 days over 7, and we distribute these frequency signals to different experiments around. Like we have an atomic fountain frequency standard that I'm inside the room right now. We have a compact standards development that I'll talk a bit more. We have a frequency comb to link to the optical domain and to be able to link to optical transitions. This is a Philips Courtet lab upstairs. And we have also another link to a telecom laser to use infrastructure fibers. This is not completely on, but we can use it to distribute frequency reference synchronized with these commercial clocks using infrastructure fibers. Okay, and we are using also some signals for local calibrations, not to certify, but to use with synchronized instruments to provide NTP servers and distribute time coordinate through internet, and to have real-time experiments or real-time performance tests in embedded systems. The contribution to BIPM is done with DNSS, Global Navigation Satellite Systems link, and then we receive and compare locally the UTC GPS that is traceable to UTC BIPM, and then we daily send back to BIPM to the NTP server. To the server in the cloud of BIPM, to FTP server, the result of the daily comparisons. We have to do comparisons, non-stop comparisons each 30 seconds to provide to BIPM. Okay, and this is maintained on all the time as we can. This central infrastructure is important because we search for rack mountable atomic frequency standards to be on almost every time, and so this is a somehow complex infrastructure. I'm not staying so much here. If someone is interested, can write to me. If not, we go longer and longer. Okay. And this is what the kind of contribution we have to maintain between plus and minus 100 nanoseconds from our local, from UTC BIPM and our local UTC. This has to be. These are some drifts that we can observe because there are some disturbance, and then we have to report, and then this is what we go. Okay. These are some applications like the NTP server that we have with sometimes 1 mega users per second taking the reference, some tests with embedded systems, and to have reliable navigation systems using the time correction for the mobile GPS or GPS receiver. Okay, this is the kind of improvement that we have when we apply these corrections. To go specifically to the compact standard, and so we go to the object of the talk. In fact, we are not talking about miniaturized standards to be like a ship, all the frequency standard, but you have a rack mountable frequency standard. Okay, so to do this, we are going to the almost fourth generation of our standard. We had some experiments and some tests of different parts to be reduced in size and mass. We had already an Allen standard deviation. This is the standard deviation that you have once you get a signal averaged during a period of time. This graph explains that when I am, let's say, 100 seconds averaging time of our frequency signal, we are already below 10 to the minus 13 of a second in resolution. Okay, and so this goes on when your sample size increase. Okay, we have been reducing size of instrumentation, the laser drivers, to be more reliable and miniaturized, let's say, but not to have a big rack for each system, but and to have some kind of motherboards that we had to develop ourselves to have it in a good performance. And we are going to have this rack mountables means 50 by 50 centimeters of size here in the transversal section, just to have an idea about this. And so one of the key components of this system are we reduce it to two diode laser systems that I'm representing as these two boxes here, these two bricks. Okay, then we go to the optical system to control frequency and temporal sequence. But this is one of the not the heaviest systems, but if you use aluminum case extended cavity diode lasers, you can have easily 1 kilogram or slightly more. Okay, because you need to have a stable extended cavity. Is a pseudo cavity, external cavity that optically feedback part of the emitted light to the diode laser, and then you control the modes, the longitudinal modes, and then you select using a selection component. It can be a diffraction grating sometimes. Then you have well-known diode laser configurations, or we are now using a very thin interference filter that's 0.3, 0.4 nanometers of line width. Okay, and then we have all the instrumentation that we are working. We can use commercial systems. We have commercial systems in the lab, and also to use as a comparison. And also we develop all the boards and for the drivers, considering temperature of the diode laser, current with low noise source, and temperature of the case, because you have to control the length of the cavity in a good sense. And we use a saturated absorption system as a reference to lock the current and the cavity length to a transition of the atoms, an optical transition. And we wanted to reduce this mass of the aluminum case. And the first, it was not really something very well planned, I should say. And I have a friend that says, Kleber, I remember he saying that printing is not a trivial operation, never. So imagine if you go to the 3D printing. And we were going to print a laser system. That's something that's tricky and has to be stable. But we could see by that time that we could have a lot of advantage. We are still under development to have it better, to improve it. So this is the first closed version that we have. And this is a monolithic block of polymer, ABS polymer. And sorry, because the dimensions were not being shown here, but we have between these hole for screws, we have 5 centimeters wide and kind of 12 centimeters, sorry, 12.5. That are the holes of the optical bench, right? So this is printed in a single block. So we don't, that's the advantage of additive manufacturing, and you can control the density of the polymer that is being printed here. So I'm going straight forward to some details. We had to mount the diode laser chip with temperature control in a small case here. We used a TO9, the 9 millimeters version, because for 850 it was not so easy to have nowadays the TO3 version with the Peltier inside, but we could reach a good mounting sub-assembly here. And then all the other components of the cavity, this is the cut view, but this is what is mounted inside the case. This small part here is to use an anamorphic prism pairs to correct or to reduce the ellipticity of the diode laser beam. And these are the components, the optical mounts, to have the interference filter, the PZT, and the mirror with an adjustment of the output coupler for the cavity, the extended cavity. Below we can see the Peltier for the case control, because we are not interested to control in controlling all the case temperature. What's important is to have the control of the laser length. This is the most important. So we had this Peltier below to control the length of the cavity, or at least to not to control, but at least to maintain it steady. Okay, these are some results that we got. This is the laser line viewed with an oscilloscope. We could see some mode holes here, and this is mainly because we are not using a very good coupling, output coupling for the end of the cavity, the external cavity. And this is a photograph of the laser that was in infrared 852. We can see it's shining some light because the intracavity power, of course, is it's bigger. And this is the exploded view of it. Some results that we could have is about the stability, the temperature stability of the laser. This is equivalent of what we have in the aluminum case, and the main difference is the base, the case base temperature. Of course, for aluminum, we have a very fast system that's 20 or less than 30 seconds, and then we got about 800 seconds for the ABS case. This is impressive. It's more than one order. It's one order of magnitude, but it's twice this. And but we got some good results when we had the laser already steady, because of course, if you compare the aluminum case that is hitting sinking heat every time during all the process of controlling, so you have to isolate. This is mainly a problem of heating control, right? So with the ABS system, you have everything already thermally isolated. So somehow it compensates the disturbance and external disturbance. So this is good in some sense. What we are going to conclude now is that still with the ABS case, in a first version, the case showed to be robust enough already in terms of mechanical stability, because we could tie it is a monolithic structure. So you make it's like in the same sense of honeycombs and such kind of system that you can tight mechanically and improve the structure. It's of course much lighter than the aluminum case, and the thermal isolation associated with the case plays a big role in the stability of the system. Because in the aluminum case, we have everything to have the fast response, but also we have to thermally isolate from the external systems. Okay, and we are doing some changes already about this thermal response to improving the mechanical project and the mechanical design. Sorry. The interference filter we manufactured also with the 3D printer, but we found that it's a bit touchy to align the interference filter, so that we are going to change also the kind of mount not to be printed. Okay, and the output coupler, the mirror, the 30% mirror that we have in the output coupler, we are going to do it with a cat's eye design that's to improve these modes jumping. So I'll stop here. I'm already getting on time, and I have to thank all the support that we have for this and for all the infrastructure that we have here for time and frequency. That's FAPESP, CAPS, CNPq, and the university too. So thank you, and Lino, I send you back the microphone.
Thank you, Daniel,
I'm
for the
going to
nice
see you
introduction.
again.
Okay, you can see now.
Yeah.
I have, but now disappear. I have two questions in the here in the chat. It's from Monica.
Okay.
Can your clock work as a reference? I mean, as a primary reference clocking for telecom networks?
Yes, even the compact clock, it can work. What we do sometimes is that we have some tests that we remove even the crystal oscillator of a board and apply directly the signal from the synthesizer. We can provide through NTP also, or I don't know if Monica is talking about optical for WDM, for example, or simply megahertz signals. But in both sense, they can act as synchronism. Thank you, Monica. So you can do it. That it can be. The intent is to have something that's rack mountable, that so you can have it in a rack of a telecom central, for example. Okay.
Right. Nilsson, if you want to open the phone, you can talk directly. We have time.
Okay, can you hear me?
Yeah.
Yeah.
Oh,
yes.
Hi, Daniel. Nice talk. The question is simple: what's the thermal expansion of the case that you developed?
Yeah. The ABS, Nilsson, is 2.5 times more than aluminum. I don't remember exactly the number, okay, but it's more than 2 times more than aluminum. But when you print, we observe that it's lower than 2.5 times, because you have it's not a dense honeycomb. You can play with it, but we changed it a bit. We didn't measure, but we got something like 2 times only. If we go to the same temperature, if you expand, if you feel the same temperature disturbance, okay. The point that I was talking is that since it's thermally, you have a thermal insulation, then it's more robust.
I see. So it's less sensitive to thermal fluctuations.
Yes, yes.
Okay, thank you.
Daniel, I should not have one question. I just have one curiosity. My experience with printing with ABS. ABS is like shrinking after printing. Did you have this problem? Why not use PLA? It's different.
Yeah, well, but the first is that we had no option of the printer that we had here. We used a more expensive Stratasys printer. That's a better resolution, but we didn't observe a shrink after the impression, the printing. But we didn't compare with PLA. Of course.
Thank you.
What was the reduction in the weight of the final assembly?
The final, if you compare only the case, is kind of 200 grams or even less. Okay. Of course, when you go with the internal mounts, then you have a kind of 5 times reduction at least.
Very good.
Thank you. We have just time for one final question. If you have someone, we have 1 minute.
And Nilson, we didn't play with the density of the honeycomb. We went to the higher density of the printer. It's almost massive in terms of ABS.
Okay.
All right. If you don't have any question, we can move on for the next talk.
Okay.
Thank you, Daniel.
Thank you, Lino.